Avenics spherical gear was invented and developed by Dr. Kazuki Abe, and now it has been improved continuously at Yamagata University. In case of a conventional gimbal mechanism, composed with three rings with different moments of inertia, its dynamic feature can be complicated and tends to have undesired oscillations and vibrations according to its unsymmetrical tensor of inertia. Cables from one actuator can hinder the smooth motion of other rings, and it tends to limit the motion range of the conventional gimbal. Its structure, composed of three rings with different sizes, is difficult to be miniaturized. Because the Avenics spherical gear has symmetrical and spherical shape, its tensor of inertia can also be simple and symmetrical, and its dynamics for control can be very straightforward with avoiding undesired oscillations and vibrations. It can be small and lightweight mechanism because it is composed of only one sphere. This is one of the main mechanical advantages of the Avenics spherical gear. Avenics is an abbreviation for active ball engagement mechanics. The unique profile of the monopole gear is designed with a virtual milling machine with the same contour of the spherical gear. By connecting dots that interfere with the virtual spherical milling machine as shown in this video, the profile of the monopole gear is designed. That is the reason why the monopole gear also has a pole structure and can mesh with the spherical gear smoothly without avoiding its poles. Three rotational degrees of freedom of the Avenics spherical gear is realized by combining rotations and twisting of these two monopole gears without mechanical interference. The rotations and twisting of the monopole gear is conducted with a differential drive. Especially, this twisting realizes three rotational degrees of freedom of the spherical gear. This video shows how twisting torque is transmitted from the monopole gear to the spherical gear. When the red pole of the monopole gear does not mesh with the red pole of the spherical gear, the twisting motion of the monopole gear around roll axis transmit torque to the spherical gear. This is the monopole gear's first degrees of freedom around pitch axis, just like conventional spur gears. If the poles of the monopole gear and the spherical gear mesh each other, the twisting motion results in only the passive sliding motion of the teeth of the monopole gear between the teeth of the spherical gear, and it does not transmit any torque to the spherical gear. But the monopole gear can change its orientation angle when the poles of the monopole gear and the spherical gear mesh together at the same point. The rotational motion of the single monopole gear realizes the rotation of the spherical gear around the same axis. So in this video, the spherical gear rotates around roll, pitch, and yaw axis respectively. When the monopole gear's pole and the spherical gear's pole mesh each other, the monopole gear can rotate passively without any power transmission from the monopole gear to the spherical gear. This passive rotation occurs when the rotational axis of the spherical gear changes from pitch axis to yaw axis in this video. With this passive rotation, the monopole gear can change its orientation smoothly. When the rotational axis of the two monopole gears are aligned to the same yaw direction, the spherical gear can also rotate around yaw axis with the orchestrated active motions of the two monopole gears around the same axis. In the right videos, the spherical gear is removed to show the synchronized motions of the two monopole gears clearly. This CG animation shows the principle of the twisting motion of the monopole gears to transmit torque to the spherical gear. The red arrows mean active power transmission, and the blue arrows mean passive sliding of the teeth. The poles of the monopole gear and the spherical gear are highlighted with yellow color. The two monopole gears are twisted together when their orientation angles are aligned to the same direction to rotate the spherical gear around the yaw axis. This passive twisting motion of the monopole gear can be possible when the poles of the monopole gear and the spherical gear mesh each other at the same point. The poles of the monopole gear and the spherical gear are highlighted with yellow color. As shown in this video, the passive twisting motion of the monopole gear without any power transmission is realized when the poles of the monopole gear and the spherical gear mesh each other at the same point. In the previous scene, this passive twisting of the monopole gears happens before the spherical gear's rotation around yaw axis. The right monopole gear in this video is rotated and twisted at the same time with its differential drive. By combining the rotation and the twisting of the monopole gear like this, the spherical gear can also rotate around roll, pitch, and yaw axis at the same time. Oblique rotational motions of the spherical gear are realized with this combined and synchronized rotations of the two monopole gears. This video shows how conventional spur gears transmit torque. This ordinary rotation of the normal spur gears transmits torque around only one axis. On the other hand, the Avenics spherical gear can transmit torque around three axes at the same time. These 3 degrees of freedom is the most significant progress of this spherical gear. These 3 degrees of freedom is realized with the engagement of the two monopole gears, activated by differential drives, and the spherical gear as an active ball joint. Various mechatronic systems can be embedded inside of the Avenics spherical gear because it can be hollow structure. For example, to utilize inner space of the spherical gear, a camera can be embedded to realize its infinite motion range and get very wide panoramic eyesight. One of the strong kinematical advantages of the Avenics spherical gear is that it has no limitation of motion ranges because it has symmetrical spherical shape. So, the finger mechanism should be embedded inside of the Avenics spherical gear when it rotates, not to hinder its infinite rotation. The flexible fingers should be extracted from inside of the spherical gear when they grasp various objects. Multiple options of the mechanisms have been examined and evaluated to design compact, lightweight, and flexible fingers that can emerge from inside of the Avenics spherical gear when it works as the end effector of the robotic arm.